Hi, welcome to the next lecture in the NPTEL series on Haskell programming. In this lecture, we'll look at a very important problem solving concept. This is a concept that it's one of the important algorithm design techniques, and this is called dynamic programming. And yeah, we'll see how you can use Haskell to tackle problems that require solutions using dynamic programming. In the next lecture, we will look at something called arrays in Haskell, which can also be used to solve this class of problems. Okay, let's begin. Let's go back to the Fibonacci numbers that we have already seen, or the Pingala numbers as they should actually be called. The program is as follows: fib of 0 is 0, fib of 1 is 1, fib of n is fib of n minus 1 plus fib of n minus 2, and fine. So, this is fine. This is one of the early programs that we saw. What is the issue? Fib n calls fib n minus 2 twice, right? Because fib n calls fib n minus 1 and n minus 2. N minus 1 itself calls n minus 2 and n minus 3, right? So, n calls recursively n minus 2 twice, and n minus 2 will recursively call n minus 4 twice, because here you have n minus 3, n minus 4, and n minus 3 itself will call n minus 4, n minus 5. So, but if you come here, n minus 2 will call n minus 3 and n minus 4, and n minus 3 itself will call n minus 4, n minus 5, and even this n minus 3 will call n minus 4. But let's not look at that for the moment. The point is that fib n calls fib n minus 2 twice, and fib n minus 2, each fib n minus 2 calls fib n minus 4 at least twice, right? So, there are a total of 4 recursive calls to at least 4 recursive calls to fib n minus 4, at least 4 calls. Now, extending this reasoning, at least 8 calls to fib n minus 6, right? And in general, at least 2 to the m calls to fib of n minus 2m, right? This is a very rough estimate, but already you can see where we are headed, right? So, fib n calls fib of n minus 2 twice, once directly and once from fib of n minus 1. Similarly, fib n minus 2 calls fib n minus 4 twice. So, at least 4 calls to fib n minus 4 and 8 calls to fib n minus 6, etc. And as I said, at least 2 to the m calls to fib of n minus 2m. The moment n minus 2m becomes 0, then there won't be any more recursive calls, or n minus 2m is equal to 1. So, if n is less than or equal to 2 to the m, recursion stops. But n is less than or equal to 2 to the m means that m is greater than or equal to n by 2. And how many calls are there? 4. So, fib n minus 2m has greater than or equal to 2 to the m calls, which is greater than or equal to 2 to the n by 2 calls, right? So, this is exponential. This is what I am trying to derive, right? So, at least 2 to the k calls to fib of n minus 2 times k. So, it appears that fib of n takes time exponential in n. This is a very rough estimate. One can actually give a more precise estimate also. If you take f of n to be the value of fib of n and g of n to be the number of recursive calls to fib 1 while computing fib of n, then you will see that g of 0 is 0 because there is no call to fib of 1. G of 1 is 1 because there is one call to fib of 1. g of 2 is also equal to 1, there is one call to fib of 1, and for all, in fact you can actually prove that for all n greater than or equal to 0, g of n is equal to f of n, because it is true for n equals 0, 1, 2, because this is yeah. So, g of 0 equals 0 equals fib of 0. And for larger numbers, for n greater than 2, from fib n there is one call to fib n minus 1 and one call to fib n minus 2, and then there are subsequent calls from those. But if you look at the number of calls to fib 1 from here, and similarly here the value is g n minus 2. So, the total number of calls ultimately made to fib of 1 is g of n minus 1 plus g of n minus 2. Okay. So, you have the recurrence g of n equals g of n minus 2 plus g of n minus g of n minus 1 plus g of n minus 2, but by induction we know that g of n minus 1 is fib of n minus 1 and g of n minus 2 is fib of n minus 2, and these two sum to f of n, right. So, you can actually prove by induction that g of n is equal to f of n. Okay, fine. So, now you know that because in this computation of fib of n, eventually you go all the way down to fib of 1 and you keep adding. Okay, that is what is happening. Effectively you are computing f of n by adding 1 to itself f of n many times. Okay, and so it takes that many number of additions also, and okay. Actually one can get precise equations for what the value of f of n is. The value of f of n is phi to the n minus psi to the n by root 5, where phi and psi are as follows. Phi is 1 plus root 5 to the 1 plus root 5 by 2, which is approximately 1.618 blah blah blah, and psi is 1 minus root 5 by 2, which is minus 0.61803 blah blah blah. So, now so therefore, it is clear that g of n being equal to f of n, and f of n is, it is clear that f of n is exponential in n, because it is like 1.5 raised to the n. Okay. Earlier we had some estimate that f of n should at least be 2 to the n by 2, right, and that is root 2 power n, and that is 1.4 whatever 1.414 power n, but this is 1.618 power n. So, this is a more precise estimate, if you will. So, any which way we have proved that the upshot computing takes exponentially many steps. Okay, and actually one can go to VS Code and check this out in a minute. But before that, let us try to figure out what is the problem. The problem, as we clearly said, fib of n calls fib of n minus 2 at least twice, right. You compute fib of n minus 2 and then you just return the value to fib of n, but if there has to be, yeah, so fib of n calls fib of n minus 1 and fib of n minus 2. Fib of n minus 1 calls fib of n minus 2. This value gets returned to fib of n minus 1, but fib of n minus 2 itself is not stored anywhere, and therefore, that necessitates a recomputation. This is a recomputation. Right, and inside fib n minus 2 there are repeated computations. so the repeated computation is being repeated even more. So that is the point. As we saw, fib of 1 is called so many times, right? So you make a recursive call, you use its result, but you don't store the result anywhere, and this is really the problem. So there are multiple recursive calls with the same argument, and this leads to wasteful recomputation. And that is why this is the problem. Actually, in the case of fib, you don't need to do all this, because you just observe and you see that, oh, there are only two values needed. Namely, fib of n minus 1 and fib of n minus 2. In fact, I will change the order. I will say fib of n minus 2 and fib of n minus 1. So at any point, if I store the previous two values, I will compute the current value, and if I compute the current value, then I can store one of the previous values and the current value, and that can be used to compute the next value. This is the idea. So just store two values always. Right, and the way you do it is that you say that you initially store 0, 1, because this is fib of 0, that is fib of 1, and you iterate the following function. So in fact, this is one maybe a strange way to do this, because all I am doing is I am doing 0, 1, right. Iterate, remember, will start with an initial value, iterate of fx, right, that is an infinite list. So we are doing the same thing here, we are starting with 0, 1, and in the next case what are we doing? If I have a b, I will switch b to the left, and instead of b I will put a plus b. So I will switch b to the left 1, and then instead of that I will put a plus b, which is also 1. Now I will switch the 1 on the right to the left, and on the right I will put 1 plus 1, 2, right, and then now 2, 3, 3, 5, 5, 8, 8, 13, 13, 21, and so on it goes, right. So the nth value, the value at index I, at index n, stores the pair fib n, n and fib n plus 1, right. So if I want to return fib of n, I will just generate this list, go to the nth element, pick the element at index n, and then that is the pair fib of n and fib of n plus 1. So I will take the first part of the pair. That is exactly what this program is doing, and as usual, laziness, right. So I do not need to, because of laziness, no need to compute the entire list. Right, you will stop at the nth index. Okay, great. So this is a smart idea you can use in the case of Fibonacci numbers. We will see that we can use a similar idea to get around this problem of wasteful recomputation in other examples as well. But before I go to the other examples, yeah, so the point is that we are looking at dynamic programming, which is a technique to make recursive programs more efficient. The key idea is this thing called memoization. Basically, it is to write a memo. So whenever you compute something, you keep a record of it, so that the same thing is asked to be computed again, you do not recompute it. Okay. And this was quite easy in the case of fib because there are only the last two values are needed, but we will look at a more sophisticated example soon. Before that, we will actually go to VS Code and we will compare the time taken by a naive Fibonacci computation and the better one which just stores two values. Okay. I am using a Go just to save some typing. Okay. So, that is my naive Fibonacci number computation. So, let me save the file and let us open GHCI here. While that is opening, here I have just replicated the same code here, iterate of this particular function, take the pair AB to the pair BA plus B, starting with the pair 0 1 which represents fib of 0 and fib of 1, and then take its nth element of this list and take the first part of the nth element. Okay. So, that is the Fibonacci program that I have. So, now I have loaded this. Let me load this okay, good. So, let us just try fib_naive on some values, fib_naive of 100. You can see that even this takes a lot of time, right, and as it should, because it should take time proportional to 2 power 100, which is like really humongous, right. So, I will stop this, I have interrupted that. Fib_naive of even 20, let us see how quick that is, okay. Fib_naive of 30, yeah, even the naive Fibonacci number computation of 30, you see that there is a sizable delay, right, appreciable delay. So, 35 or some such, and you will see that the delay is much more. Yeah, in fact, you should try this out on your own and see how long it actually takes. I shall interrupt this, and instead of this, I can say fib of 100,000. Yeah, you see that you get the result extremely quickly, right. Fib of 35, just in case. Okay, fib of 35 was instantaneous, but fib of 100,000 was also very quick. Fib of 10,000 even quicker, right. So, you see that this other solution, it just takes order n time where n is the size of the, not the size, n is the actual value of the input when you say fib of n. Okay, good. So, this illustrates that you know how much savings you can do with when you avoid wasteful recomputation. Even fib_naive of 35 took forever to compute, but fib of 100,000 and all is getting trivially computed, right. So, okay, so I hope you appreciate the difference in the two programs, and it is purely algorithmic. There was nothing, there was no Haskell trick or anything that we applied. We just observed that some computations are being done wastefully and we want to avoid that. Okay, let me get back to the slides. Let us look at a more sophisticated example now. So, this is the problem of finding the longest common subsequence. Okay. Okay. So, given two strings A's and B's, I want to find the length of the longest common subsequence, okay, of A's and B's. What is a subsequence? Suppose I have a string. A subsequence is one where I would just take this, maybe this, maybe this. Okay, I should have used a different color, but that's okay. And I take these in order. Okay, maybe there are two characters here, 3, maybe 15 here, 2, 1. Okay, I will take all these in order. That's a subsequence. So if I have then I'll maybe B A A D R A. Okay, so that's a subsequence because I took here, 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 and here. Okay, so there's a difference between subsequence and substring. Substring means it should be contiguous. Subsequence means I can skip elements and pick a and retain the rest. That's a subsequence. What is a common subsequence of A's and B's? It should be a subsequence of A's. It should be a subsequence of B's, and also longest common subsequence of A's and B's means it is the longest string that is simultaneously the subsequence of both A's and B's. Okay, so this is what we want to compute. We want to just compute its length for the moment. Okay. Okay. So essentially we would like to write the Haskell program LCS. LCS of some AGCAT and GACT should be GAT is the subsequence that is common to both, and the length is 3. LCS of LeBron James and Michael Jordan should be, there is this E here, there is this E here, and then there is this J A space J A. Okay, so that is the subsequence, and the length is 4. Okay, you get the idea now. What is the strategy to compute length of the longest common subsequence? Okay, if the first letter is the same in both strings, then that letter always belongs to the longest common subsequence, right? Because if you had some other the first, so if so I have A's here, I have B's here. If I included one and not the other, but anyway the common subsequence would have started somewhere here and this is equal to that, right? Instead of choosing this, I could have chosen this. Okay, so the first 2 letters are the same in both strings, that will always belong to the longest common subsequence. And if I did not choose either, then the longest common subsequence starts from somewhere here, but that's a contradiction because I can always extend any common subsequence that comes later by adding this first letter in both the strings, right, in both the subsequences. So in any case, the upshot is that if the first letter is same in both strings A's and B's, then that letter always lies in the longest common subsequence. Otherwise, you have to do 3 subcomputations. You have to either skip the first letter in A's or the first letter in B's, or you have to skip both first letters. Okay, and you have to compute recursively and then compare and choose the best. Okay, so that is the point. So here is the naive algorithm to compute the length of the longest common subsequence. I have LCS, which is of type string arrow int, right? LCS of, if I have the empty string on the one side, then it doesn't matter what the other thing is, the longest common subsequence is the empty string whose length is 0. LCS of anything empty string is also 0. LCS of x followed by x's and y followed by y's is, I have to anyway make 3 recursive calls: LCS of x colon x's y's, LCS of x's y colon y's, LCS of x's y's. Okay, I don't need to always make this. I'm just telling you that it is possible. It's possible that you make up to 3 recursive calls, and then on those values you apply this update function, update of x, y, and 3 numbers. Okay, so this update is of type char arrow arrow int arrow int arrow int int arrow int arrow int arrow int. Okay, so this is x, that is y, this is that's m, this is n, that's p. Okay, that is the type of update. All you do is the following: if x is equal to y, then you have to choose 1 plus, you have to skip both the first letters, both the first letter in A's as well as in B's, and then you have to do the recursive computation. So, you actually do, if x is equal to y, then 1 plus p, where p is LCS of x's y's, right. If x is not equal to y, then you independently compute this. Here you are skipping the first letter in y's, here you are skipping the first letter in x's. You compare those two things independently and then you compare and pick the maximum of the two. Okay. So, this update function just says if x is equal to y, then 1 plus p, else max mn. I have programmed this as LCS naive. Before we move to the sophisticated strategy, we will look at how much time this takes, an estimate, and then we will look at how the program runs. Okay. So, this takes time exponential in the sum of the lengths, so clearly because there are multiple repeated calls. Yeah, because same problem as with fibs, many recursive calls are repeated with the same arguments. Yeah, so one more thing is that if you just compute the lengths, that is fine, but you can also actually compute the actual string. Okay, this is the actual, this is some subsequence, some common subsequence of longest length, largest possible length. Okay, fine. So, so if I have empty string and anything else, the longest common subsequence is the empty string. If I have anything and the empty string, the longest common subsequence is again the empty string. If I have x colon x's and y colon y's, then again it's the same structure, update xy, LCS x colon x's y's, LCS x's y colon y's and LCS x's y's. But here what we do is update xy tu v, t is a string, these are all strings. So, now in this case update is of type char arrow, string, arrow string, arrow string, arrow string, right. This is this. Okay, okay, fine. But what is the computation itself? If x is the same as y, then you have to retain that x and you put it in front of v. What is v? V is LCS of x's y's. Okay. Otherwise, you check if length of t is greater than or equal to length of u. In that case, you take it to be t. Otherwise, you take it to be u. Okay. So, this is a simple enough computation, and you can do this. If you want to do some little optimizations, you can actually say, rather than compute length of the thing every time, you can actually store the length along with the subsequence, and this go will be of type string command. Okay. So, so second of, okay, int comma string. Right. So, go of empty list, anything is 0 comma empty list, go of anything empty list is 0 comma empty list again, go of x colon x's and y colon y's is again the same structure here. Same structure as earlier, but now this update xy and mt is a pair, these are all pairs. Okay. And I have p comma v, p is a number and v is yeah, p is a number and v is a string. So, if x is equal to y, then I do 1 plus p comma x colon v, else if first of mt is greater than or equal to first of nu, then mt else nu. Okay. So, this is just the same thing with some minimal optimizations if you want, so that you avoid length computations repeatedly. But that does not save much, because you anyway have to keep making recursive calls with the same arguments repeatedly. Okay. Okay, so let's actually go to VS Code and check out how much time this LCS takes. I have an LCS naive here, which actually computes the longest common subsequence, and here I use the same strategy as storing the length and the subsequence. Yeah, so yeah, right, it's essentially the same program with some minor modifications, just syntactic more or less. So let's compute LCS naive of, do I also have some routines to, let me copy these uh, functions to generate random strings. Okay, I am now copied this. Let me save this. Let's get back to GHCA. Let's reload this function, this program. Okay, so now I have LCS naive of, I don't before that let's generate a random string. A is equals rand string of, yes, I am just giving a length. Okay, so rand string of length, I don't know, 30. B's is a rand string of length 30 again, let's say 35, whatever, doesn't matter. Let's see what A's is. Okay, let's see what B's is. Okay, let's actually try LCS naive. It should take a very long time. Okay, so sorry to have chosen a bad example. I can actually try first LCS naive of the example that I gave earlier. Even this takes a lot of time, right? And what is the this thing between LeBron James and Abdul Jabbar? It is just JA. So it should be length 2. It should be just the sequence JA. But even that takes so much time to compute. And LeBron James is a string of length 12, and Abdul Jabbar is a string of length again 12. And even this is taking a lot of time, right? So let me abort this. I have a normal LCS, the non-naive LCS, so which I can try it on that as well. Yeah, this thing returns immediately, not just on this, but also on the other thing, right? Yeah, it was extremely quick. Okay, so how did we make so much progress? Okay, we'll see that in the slides, right? And in fact, I can even choose my A's and B's to be much larger strings. A is, let's say it's a random string of length 100. B's is another random string of length 100. What is A's? Something long like this. What is B's? Some other long string like this. I can ask for LCS of A's, B's, and in a jiffy I get a result. Okay. Okay, let's look at how what the improved program is. Okay. So let's get to the improved solution in stages. What are the recursive calls made on the way to computing LCS ASBs? You have LCS use V's for every use in tails of A's and every V's in tails of B's. What is tails of A's? Yeah, tails of A's is all. So if I have, let's just look at an example. Yeah, I think it should go in this order. I think it is in this order, but you can actually check in VS Code. Yeah, it's the same, whatever I told. The whole thing is a tail for our purposes. It is all suffixes really. Okay, so that's what I have. So really, because to do LCS, if I have two strings, I'll do LCS this whole thing, but then I might have to do I might have to compute LCS of this string with this string. Okay, this and this. I might have to compute LCS of the whole string with this, LCS of this whole string with that substring, and so on and so forth. So essentially, you will consider all possible suffixes for A's, consider all possible suffixes for B's, pair them up in any which way, and then you have to compute the LCS of them. And of course, you will have to compute them from smaller lengths to larger lengths, so that you can use the recursive values. Okay, but essentially you will end up computing all these values, and there are, like, if A's length of A is equals length of B is equals n, let us say, there are n plus 1 the whole squared recursive calls, the calls in all. Ideally, what we would like to do is, in n plus 1, you are computing n plus 1 the whole squared values, you should store them in some organized manner and be able to extract the pre-computed values and use it in subsequent computations. Okay, this is what we aim to do. Let's see how to do this. So tails is the following. Tails of empty list is just the singleton list containing the empty list. Tails of x colon x's is x colon x's followed by tails of x's. Okay, so this is the thing, all suffixes of x's. So strategy for computing LCS of A's B's is, for any suffix x's of A's, compute row of x's, which is LCS, which is a list of values, right? LCS x's V's, where you fix one of the suffixes of, fix the suffix of x's, fix a suffix of A's, compute LCS with respect to x's and all suffixes of B's. Okay, so okay, suppose you do this, then what? Yeah, then you can use, the idea is to use the list row of x's in computing row of x colon x's, right. So, this is the idea, and the final answer is the first element of row of as, okay. Okay. So, a picture will help. So, if I set out this is S, right, and if I consider 0, 1, 2, 3 dot dot dot, okay, and what is the cell entry here? It is LCS of drop I S, right. That is another way of getting a suffix, right. You drop so many elements, you will get a suffix. Drop 0 means the original list itself. Drop n means the empty list, right. So, at any at row I and column j, the value you have is LCS of drop I A's and drop j B's. And now, as we know, this drop I A's and drop j B's, to compute this, you need to know the value to its right, the value to the bottom, and the value diagonally opposite, okay. So, this is LCS of drop IAS drop j plus 1 B's, etc., etc., okay. So, this is, yeah. So, you get the idea. So, essentially what we are doing is you are trying to fill in a matrix, and you have to fill in the matrix from the bottom right, because from the bottom right, and fill in the bottom row first and then keep going up, okay. So, it should be easy to fill the bottommost row, it should be easy to fill the rightmost column, and then once I have these two, then I can fill in the other, because any entry depends on the entry to its right, to its below, and to the diagonal below, okay. So, this is the idea. So, you want to fill it up in this systematic manner. In other programming languages, you would use arrays to do this. You can use arrays also in Haskell to do this, which we will see in the next lecture. But without even going to arrays, just using pure whatever the basic Haskell that we learnt and lists, you can actually achieve this. The point is that if I have the whole row below, I can compute the so if I have the whole row here below, I can compute the row above, okay. That is the point, okay. So, the program so far that as we have outlined the strategy is to say that LCS AS B is equal to n, where n followed by whatever is row of A's, okay. Row of empty list is init row, which is the bottommost row in our picturization, and row of x colon x's is you compute the next higher row. In fact, I will say next higher row, right. And in computing this, you might need some auxiliary information, you might need all information about B's, you might read the previous row, and you will need what x is, okay. Use all this to compute the next higher row, okay. What is init row? Init row is LCS of empty list V's, because row of empty list, where V's comes from tails of B's, but LCS of empty list and anything is 0, right. So, it is 0 repeated how many times? As many elements there are in tails of B's, but tails of B's, length of tails of B, so its replicate length of tails of B's time 0, but length of tails of B's is B's plus length of B is plus 1, okay. So, replicate length of B is plus 1, 0, okay. So, it is the row 0, 0, 0, 0 and okay, so many elements, okay. That is my bottommost row. So, the next row function should recurs on the second argument. The next row function has two things, right? So it takes the complete previous row and it takes the extra letter in this row, right? X colon xs. I should do something, and essentially what do I want to do? I want to compute the LCS of x colon xs with respect to everything in tails of B's. So it would suggest that I have to do a kind of recursion on B's starting from the rightmost element of B's and going to the left. So let's try that. So the base case is simple. Next row x of empty list. Okay, so this is the last suffix of B's equals the last element in tails of B's. Okay, so next row of x empty list, row of x's. What you want to compute is LCS of x colon x's with respect to V's, where V's comes from tails of empty. Okay. Yeah, but tails of empty is nothing but singleton list containing the empty list. So if I try to compute V's from tails of S's, it is just this, okay, just the empty list. But LCS of anything with respect to empty list is 0, so I have a singleton list consisting of 0. Okay, so what I am doing is I want to compute next row of x with respect to B's and row of x's. Okay, B's itself is some large thing. I will do this induction on the suffix of B's. So I will first compute next row. So do this by saying next row of x empty list. So let's say B's is actually B1 to Bn, right? So next row of x of empty list with respect to row of x's. Okay, I will compute this in order, and at the end I will have next row of x of B's of row x's. Okay, this is the kind of recursion I will do, and the first value is clear. This is next row of x and empty list row of x's is nothing but empty list. Okay, sorry, 0, because that is the length. So the induction step is next row of x y colon y's, right? So if I want to write it in terms of that picture, I have next row of x, and here I have some b I. Okay, so this is what I want to compute, and I want to compute it with respect to next row of x bi plus 1 dot 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 bn. Okay, that is what I am motivating here. So this is LCS of x colon x's v's, where v's comes from tails of y colon y's, in this case bi dot 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 bn. This is LCS of x colon x's y colon y's, because the first element of tails of y colon y's is just y colon y's, followed by LCS of x colon x's v's, where v's comes from tails of y's. So this is nothing but LCS of x colon x's y colon y's followed by next row of x y's, what? Same row of x. Yeah, so here is where one has to make a decision. Is it same row of x's or is it something else? Okay. In fact, I had kept on saying that you should use row of x's, but that's not clear. Okay, and in fact, it won't be row of x's. It will be different, as we will see in a minute. Right. So what should be the third argument in the recursive call? Let's look at it. So LCS of x colon x's y colon y's is given by update of xy, LCS of x colon x's y's, LCS of x's y colon y's, LCS of x's y's. But LCS of x colon x's y colon y's is rho of x colon x's at 0, and LCS of x colon x's y's, we will come to that in a minute. This is rho of so this is rho of x's at 0, and this is rho of x's at 1, okay, and so this is assuming y colon y's is the whole of b's. Then we are doing this, and then we will extend this logic, okay, for the general recursive calls. So then of course this is rho of x's at 0, rho of x's at 1, okay, that is these two values. What about this value? This is not rho of x's, this is rho of x colon x's, which we are building, and we somehow want the this thing, and you will see that rho of x colon x's at 1 depends on rho of x's at 1 and rho of x's at 2, okay. So that is the point. So this is the thing, rho of x colon x's at 0 depends on similarly, if I switch it, rho of x colon x's at I depends on rho of x's at I and rho of x's at I plus 1. Right. So this is the point. So I have a row of x's that I have already computed, but as I make recursive calls, I should actually take suffixes of row of x's as well. This is the idea, because as you keep taking suffixes, you will identify. So this is I. This is row of x colon x's. This is row of x's. This depends on this as well as that. But how do you, we do not want to randomly go on index by saying bang bang, but if I am trying to compute this, what I want is just that part of row of x's. So what I do is, when I make the recursive call, I will just pass the tail of my original thing as an argument, okay, as you will see here in a minute. So these are row of x's at 1 and row of x's at 2 are the first two elements of tail of row of x's, okay, because it's x's of 0, x's of 1, x's of 2. So you should pass that argument such that you can recover whatever elements you need by going to the first element and second element, okay. So based on this logic, therefore, I have tried very hard to give the intuition for this. Based on this logic, what you should actually do is this, okay. Next row of x y colon y's is nothing, is LCS of x colon x's followed by y colon y is followed by next row of x y's, instead of y colon y's I have y's here, tail of row of x's, okay. So this is the important point, okay. Okay. So finally, putting all this together, I have this program LCS of ASB is equal to n, where n is the first element of row A's, row empty list is init row of x colon x's is next row computed using x, b's and row of x's. So I am computing row after row. Init row is replicate length bs plus 1 of 0. Next row of x, if b's is empty list, so then I will just have this singleton list containing 0. Next row of x, y colon y's, and I can actually do some optimization, because I know that next row of x empty list, the next row of x whatever list you want to compute will have one more element than the length of that list. So, I can assume that since the list here is y colon y, I know that the here it will be n colon p's. So, I will say let m colon m's equals next row of x y is p colon p's. Okay. Yeah. So, I want to compute this. Yes, I want to compute some value here, right, and this depends on to make the recursive. So, I need to compute this value based on the value to its right, based on the list to its right, and to compute the list to its right, I will actually do next row of x, this is y colon y. I will actually do next row of next row of x y's. Okay. So, let me change color. This whole thing is y colon y's. This whole thing is y's. Okay. So, to do this, I will do next row of x y's. I will make a recursive call to the suffix on the right. But when I want to pass this thing is actually m followed by n followed by n followed by p followed by p's. So, when I make the recursive call, I will make the call to p followed by p's. I will take the tail there. Okay. That is the tail of whatever was the third argument before. Whatever argument this is the tail of that. Okay. And that is basically it. So, I will do that and that will give me some value. This whole thing is what I want to call this the result of this whole list, this list of numbers associated with this. I have a list of numbers which I want to call m followed by m's. Okay, so associated with y's. Okay, and what I want to do is I want to get a new value based on this m, this n and that p. Okay, that is basically what I want to do, right. It is this, I want a value here and the value depends on the value to the right, the value right below and the value diagonally below. Okay, so m and n and p. So, this is basically the algorithm. It is the same update function except now I am calling it an extra function. I am computing things row after row. Okay, and if I do this is a very optimized version of the program, and I urge you to just study this and try to understand it in better detail. Okay, so this is this idea is courtesy. This is from the book Bird and Gibbons. This is a delightful book which tells you how to have very efficient algorithms in Haskell, just following basic Haskell programming, but using very smart ideas like this. Okay. Okay. So, here is a version where I actually compute the, we can actually introduce some folder and some other optimizations and actually get a program that looks like this. Yeah. So, n followed by something is folder of next row of init row is, okay, and init row is this, next row function on x equals go of b is where I mean, so it is the same earlier program where I have optimized a little for to just make it more compact, and I can also compute the actual subsequence by the same logic. Okay, so instead of storing just a number, I will store a number and the subsequence, and in this case now I will say that, oh, the number comma subsequence is the first element of this sequence of this computation, and init row is basically this. I replicate 0 comma empty list and go here also you will see that the rightmost row is 0 comma empty list, the rightmost value, the rightmost column, and then the rest is a very similar computation. And now let us actually see this in action. Okay, we have right, so we have the same thing programmed here. Okay, LCS naive, that's LCS naive. The actual LCS is programmed here in precisely the manner that was stated in the slides, and this is the program that actually performs so well even on large numbers. Okay, I can even do something like rand string of I don't know, A is rand string of 1000, let's say. Okay, so I have B's which is a random string of length 2000 and A's which is a random string of length 1000. Let's clear the screen and see what A's is. A's is some humongous long string, B's is some even longer string, and now I can actually say LCS of A's B's. Let's see. This should still take time because but it didn't, right? Before I was done speaking, it produced the result. And remember, it's a 1000 length string and a 2000 length string, and even then you are able to produce very quickly the longest common subsequence. Okay. How do you check that this is indeed the longest common subsequence? That's something that you can actually program and try to test for your own. I'll leave it to you as exercise to do that. Okay. So essentially what I want you to do is, given 3 strings, check whether the first string is a common subsequence of the other 2, and furthermore check whether the first thing is, whether there is that would require you to do this LCS computation. The simplest way to do it would be to do the LCS computation and check whether it is equal to that string. So this is something that you can do, but yeah. If you think of a better way, you can do that yourself. Okay, that is true. Once I have computed the LCS, to check that it is an LCS. Okay. Okay, fine. So now let's move to a different problem which faces the same kind of thing. This is an interesting problem. Longest ascending subsequence, it is called. Find the longest ascending subsequence of a list of integers. Okay. Once again, it is the, so let's say that go L is the longest ascending subsequence starting with L 0, the 0th element of L. So it is convenient to take go of empty sequence of empty list to be the empty list. Okay. So we'll assume the following function. So longest, let's assume that we have the following function. Longest is a function that takes a list of integers and gives you one list of integer. Longest of the singleton list, longest of a list which consists of only one list is just that list. Okay. I shouldn't have put this here. This is wrong. It should just be L. Okay. Longest of L followed by L's is, let L prime be longest L's in if length of L is greater than or equal to length of L prime, then L, else L prime. Okay. So this is just some simple find element of maximum length. Okay, that is what we are doing. So now you can define your LAs of A's, longest ascending sequence of A's, as longest of map go tails A's. Okay, because go is the right. So what are we really doing? What we are doing is that we have A's, right. So you find the so you can find the longest. So you have this empty list also. So yeah, so you have longest ascending subsequent. So let's say A's is A1 to AN. Okay, you compute LAs of the list AN, LAs of empty list, go of, I should say, what is the point? The point is that the longest ascending subsequence in your in your list has to start with some element, okay, and it will either start with element 0 or element 1 or element 2 or element 3 or whatever. So, remember that go of L is the longest ascending subsequence, that should definitely include, yes, go of A is, go of any use longest ascending subsequence of U colon U's, that must definitely include U. This is the point, right. So, I am computing for every for every suffix, I am computing the longest ascending subsequence that must start at the first element of that suffix, and my longest ascending subsequence of the overall list is the maximum, the longest list, right, among all these lists, right, because the longest ascending subsequence I do not put any constraint on where it should start, but if I now consider, but it has to start at some index I. If I have already computed the longest ascending subsequence starting with index I for every I, then I just take the maximum of those and that will be my answer. So, this I can do, okay, sure, I can do this. So, to compute go of x colon x's, collect all go v's such that v's belongs to tails of x's and filter out the ones whose head is greater than x. Yeah, so here is the point. So, how do I, suppose I already have go x's for go v's for all v's in tails of x's, right, then so to compute my this thing, find out the, filter out the ones whose head is, because what do I want to do? I want to pick a longest an ascending sequence subsequence starting at some later index and stick x in front, right. But this is the result will be an ascending sequence only if x is less than the start of that ascending sequence, I do not know, call it ascending subsequence, call it S, let us say, right. I can stick x in front of s only if x is less than the start of s, which is why once I have the go values for everything after x's, so I will filter out all those ones whose head is greater than x and attach x before the longest element among these lists, okay. And what does that computation entail? So, you get this very simple recursive program. LAs of longest ascending sequence of A's is longest of map go tails of A's, where go of empty list is empty list, go of x colon x is x followed by longest of L such that L belongs to L is an map go tails of x's, right, and ascend xl. Ascend xl is nothing but saying that ascend anything of empty list is true, ascend x of y colon whatever is xl is just to check whether x is less than y, right? Can I actually attach x in front of L and form an ascending sequence? That is what this ascend XL asks. Okay. Now, once again there are repeated computations to this Go, there are again repeated computations to go with the same argument, okay, and this is a problem. Okay, you will have wasteful recomputation. To avoid this, we can do a nice trick, which is that map Go of tails x's is used repeatedly. So, you redefine Go to not return one. Earlier we defined Go to mean sorry, let me go back. Yeah, Go was defined to be this one subsequence. Now, you define it to Go's well should be a list of subsequences one for each V is in tails of it, right? That is the point. This whole map of Go of tails of x's, you take it to be one function, and if you do that, then the full program is just this ridiculously simple program. LAs of A's equals longest of Go of A's, where Go of empty list is the list containing the empty list. Go of x colon x's is x followed by longest of the same computation that we had earlier. First you do Go of x's is else, let us say, you take else and then you stick this new longest ascending sequence in front, okay. So, this Go of x's will give you a list, lots of sequences, one sequence followed by another sequence, followed by another sequence. This is this big list, okay. Go of x's itself is a list of lists, okay. The inner lists are all various ascending sequences starting at that particular index of x's, but this is all you need to do, and doing it this way you have it's extremely efficient, because Go of x colon x's just makes one call to Go of x's, and that already contains all information that you need. You just need to process that list, okay. This is the idea. So, let us just show how it runs in VS Code, and then we can end this lecture. You can introduce some fold down and optimizations, and the runtime is order n squared, because you are computing, you are making n recursive calls. Each time you make a recursive call, you do some order n kind of operation, because you are doing some operations on that whole list, you are doing some filter, etc., etc. Okay. Okay, so that's basically it for this lecture. I will go to VS Code and run this program, run a couple of examples, and then we can end this lecture. Okay, so I have so I have LAS naive here. I have LAS, which is longest is this function, longest of singleton L is L, longest of L colon L is whatever this thing is, ascend is that, and LA, I have even a derivation here. LAS is actually goes of longest of goes of A's, where goes of empty list is singleton list containing the empty list, and goes of x colon x's is let LS equals goes of x's in this whole thing. The important thing is this, the last line, I am computing something and putting it before else, okay. So, that's the point. Let us just try to run it on some random list of integers. I should say n's x's. Rand int list of length 100, let us say. Okay, now I need to find the longest ascending subsequence. I can just say LS of x's, and I get something, okay. So, clearly this is ascending, right, and this is the longest, if you have to believe this program. And I think that is it. It was we have shown some couple of very important issue which happens when you do recursive programs, which is that the same value will be recomputed many times, that is wasteful. So, dynamic programming is a technique where you just remember these intermediate computations somehow and the next time you have to do the same computation, you just use the stored value rather than recompute it directly. And even though in Haskell we do not have actually the notion of variables like in imperative programming languages, where there is some location in memory and you store a value in that location which you can later read, etc., you can still do quite a lot, because you can use some local names to refer to lists and store enough information in terms of lists. Okay, so accumulate enough of the previous subcomputations, and that will let you do the subsequent computations easier. And all this goes back to, all this is, the germ of all this is found in the fib program which I show here, where you actually store two values instead of one, and you don't need to necessarily store this value in a variable and retrieve it, etc. You just keep carrying some intermediate values. Okay, that's basically all you need to do. And this is a very clever way of tackling this problem and making programs more efficient. We will in the next lecture introduce arrays, where you can do many other things, and it's a generally a good thing to know. It is not part of basic Haskell, but there is a nice array library. We'll look at that, and we can also solve these kinds of dynamic programming problems using arrays. That is in the next lecture. Thank you for now.